Welcome to qnawire.
Chapter 16, Problem 122. What is the boiling point of a 0.1 molar solution of NaOH HSO4 if the solution has a density of 102 grams per milliliter? One thing we're going to assume is that we're going to be dealing with a 1 liter solution. So when we're doing this, we're going to be dealing with 1 liter. So 1 liter is also equal to 1,000 milliliters, and we can figure that out by doing 1 liter over there is 1 liter for 1,000 milliliters. So now since we know that, we can find out how much is the weight of our solution. And to do that, we know that density is equal to the mass divided by our volume. And we know that we're going to be using 100 milliliters. So our density will be D times V equals M. And we have 1.002 grams per milliliter times 1,000 milliliters. And then we get the mass of the solution to be 1,002 grams. And this is for mass of solution. Next, we're going to find the mass of the solvent in the solute. And to do that, we need to know the molecular weight of NaHSO4. And to do that, you just add up the molecular weight of each of the compounds. So Na plus H plus S plus 4 oxygens. And when we do that, we get a molecular weight of 20.055 grams per mole. So to be able to determine the molecular weight of the solute, we are going to mean the mass of the solute. We then are going to take this molecular weight and use our molarity equation. So we have moles over liters is equal to molarity. We already know our molarity and how much we are starting with will equal to our moles. So from there, we can find our moles. So we're going to have 0.10 molarity times 1 liter, which will equal 1 mole. And then that number is going to be 0.10 moles. Now, since we know how many moles we have, we can calculate how many grams of NaHSO4. So we do 0.10 moles of NaHSO4, and then you just go through your molecular weight. And so you know you have to multiply them, and you're going to multiply by 20.055 grams over 1 mole. Our moles cancel out, and so we only have grams left. And so therefore we will have a total of 12.055 grams, which is going to be your mass of your solute. Now to find the mass of the solvent, we are going to have an equation of your solute plus solvent gives you your solution. We know our solution weight and we know our solute weight, so therefore we can find our solvent. So the mass of solvent is equal to your solution mass plus minus your solute mass. And we found in the very beginning that our solution was 1,002 grams. And the last part, we just found our solute to be 12.055 grams. Now we would just plug that into our calculator, and we get a mass of our solvent to be 989.9 grams. And from there, we're going to use that in a little bit. So next we also need to figure out the concentration of our ions. And so for us to be able to do that, we're going to have to write out an ice table equation. And to do that, we know we have H in a HSO4, and that's going to completely dissociate into Na plus and HSO4 minus. And since Na is not going to play a role, we're just going to have our HSO4. And then we're going to use that for our equilibrium table. So then we're going to have an H plus an SO4 2 minus. And then we just do ice from there. We know we had an original concentration of 0.1 molar, and then we had 0 for our other two starting solutions. Then we subtract from the initial and then add to the other side. And then for the equilibrium, you just add up the two rows before. And so we get 0.1 minus x, and then x and x for our other two items. We also know our Ka value is going to be 1.2 times 10 to the negative second for this solution, and I just found that in the back of our textbook. And then so the equation for Ka is products over reactants, so we're going to have our H plus concentration times our SO4 2 minus concentration all over our HSO4 minus concentration. And when we plug that all together, we get 1.2 times 10 to the negative 2 is equal to x squared over 0.1 minus x. So I'm going to take this to the next page. What I just wrote was 1.2 times 10 to the negative 3 is equal to our products, which was x squared, over our reactants, which was 0.1 minus x. And now we need to solve for x. So to be able to solve for x, we have to get all of our equations equal to 0. So what we're going to do is we're going to multiply 1.2 times 10 to the negative third by 0.1 minus x is equal to x squared. When we multiply that out, we get 1.2 times 10 to the negative fourth and then minus 1.2 times 10 to the negative third x is equal to x squared. Now we're going to bring that x over, and so then we're going to have 0 is equal to x squared plus 1.2 times 10 to the negative 3x minus 1.2 times 10 to the negative fourth. All right, so now since we have that entire calculator, we will then solve for x. We know that a is equal to 1, b is equal to 1.2 times 10 to the negative 3, and c is equal to negative 1.2 times 10 to the negative fourth. We're now going to use our quadratic equation, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's what x is equal to. So whenever we plug in our values that we just found for our a, b, and c, which are our coefficients of our equation up here, we will get negative 1.2 times 10 to the negative 3 plus or minus the square root of 1.2 times 10 to the negative 3 squared minus 4 times 1 times 1.2 times 10 to the negative 3 negative all over 2 times 1. All right, and when we plug that into our calculator, All right, we get our X to be 0.0103. Now, since we know what our X is, we can then find our concentrations of our other values. And so we know from our ICE table that we saw on page 2 that X for the Na plus and HSO4 are equal to each other. And so we know those concentrations, but then the equilibrium concentration for NaSO4 is going to be 0.1 minus what our X value was. So the HSO4 minus is equal to 0.1 minus 0.0103. Our H plus is equal to our SO42 minus, and that's just equal to 0.0103. Now we then are going to use that information to help solve for the molarity of our HSO4. So 0.1 minus 0.00103, we get 0.098 of our HSO4 minus concentration. So now since we have that concentration, we're then going to find the total ionic concentration. And to do that, we are going to just add up the concentrations of all of our ions. So to do that, we have the Na plus ion we have to add, plus our HSO4 ion, plus the H plus ion, and the SO42 minus ion. So we know that Na plus is 0.1 because that was from its original concentration. We know our HSO4 minus is 0.09. And then our H plus and SO4 are the same, and that's 0.0103. Now when we add those up, we get a total ionization constant of 0.209. Molarity. So now since we know the molarity of the ion solution, we can find our molality, and our molality equation is equal to moles of solute times 100 over mass of solvent. And to find our molality, we already know what our moles is, and that's what we just found above. So 0.209 times 1,000 grams to make it to kilograms over our solution that we found in the very beginning of 98.9 grams. We got the 209 molar solution to moles by saying that our molality is equal to moles over liters, and we know that we had 1 liter, so molarity times liters equals moles. And when you do that, you get this same number. So now when we plug that into our calculator, we will get our molality, which is a lowercase m. And we're going to get 0.2114 for our molality. Now, since we have our molality, we can use that in our equation of the boiling point temperature. So delta TB is equal to your KB times M, and lowercase m is your molality. When you look up in the back of your textbook, your KB for the solution is 0.51 degrees Celsius over molality. So to find our temperature that our solution is going to boil at, we do 0.51 C times our molarity solution, which was 0.2114. And when we plug that into our calculator, you get a delta T B of 0.1078 degrees Celsius. So now, since we know our boiling point is what our boiling point addition is going to be, we know that we are mostly in water. So we're going to take water and find what our final concentration is. So delta TB is equal to your T final minus your T initial. And we're trying to find the TB. So to do this, we also know that the boiling point plays a role in the temperature of the solvent plus the delta TB. So our solvent is water, so we know that boils at 100 degrees Celsius, and then we found that our delta TB was 1078 degrees Celsius, and when you add them together, you get 100.12 degrees Celsius.